Have you ever stopped to think about what truly powers the sun? Or, how scientists can date a fossil that's thousands of years old? Or even how we could possibly create entirely new elements?
Mm.
Today, we're taking a deep dive into nuclear chemistry. It's a field that often sounds incredibly complex, but it's actually full of surprising facts and really fundamental insights into the nature of matter and energy. Our mission is to give you a clear, conceptual understanding.
It is remarkable, isn't it, how nuclear chemistry really challenges our everyday assumptions about the world. When we talk about these kinds of reactions, we're discussing transformations on a scale just, well, far beyond what we typically see.
Right.
And this distinction, the fundamental difference between ordinary chemical processes and these unique nuclear reactions, that's going to be a core theme today.
Okay, so let's start with something fundamental. Radioactivity. At its heart, it's the spontaneous emission of particles or energy from an unstable atomic nucleus. And here's a wild fact from our sources. Every single element with an atomic number greater than 83 is naturally radioactive. That means a huge chunk of the periodic table is constantly, transforming.
That's a crucial starting point. It immediately highlights a key difference. Think about everyday chemical reactions like, say, burning wood or mixing baking soda and vinegar.
Yeah.
In those cases, atoms are just rearranging. Bonds break, new bonds form, but it's only the electrons in their outer shells, the orbitals, that are really involved. The energy changes are, relatively speaking, pretty small.
Okay.
And you can easily speed them up or slow them down with temperature, pressure, catalysts, all the usual tricks.
Right, like turning up the heat to cook something faster.
Exactly. But in nuclear reactions, we're talking about the nucleus itself undergoing a profound change. One element can literally become another element, or, at least a different isotope.
Whoa.
We're dealing with protons, neutrons, electrons, even other subatomic particles. And the energy released or absorbed is truly immense, just orders of magnitude larger than any chemical reaction. And critically, the rates of these nuclear transformations are generally unaffected by those external conditions. A radioactive atom decays when it's ready. It doesn't matter how hot or cold it is or what pressure it's under.
That's a really wild difference. So if we're literally changing elements, how do we even write an equation for that? How do we balance it?
Well, thankfully, the rules are actually pretty elegant.
Okay.
The total number of protons, that's the atomic number, and the total mass number of protons plus neutrons, they have to balance on both sides of the equation. We use simple symbols. A proton is H or P with mass 1, charge 1. Neutron is N, mass 1, charge 0.
Got it.
Electron is E or beta, mass basically 0, charge -1. A positron, its antiparticle, is E or beta, mass 0, charge +1. And an alpha particle is alpha or helium, He, mass 4, charge 2.
Okay, so it's like accounting, but for nuclear particles.
Exactly. The beauty is the underlying principle of conservation. You're conserving the total stuff in the nucleus, even as it transforms. Now, there's a subtle distinction sometimes. An electron from an orbital is usually E, but one that comes from the nucleus in decay is specifically called a beta particle, often written as BAFE.
Right. Okay. Beta particle.
Let's take an example. Polonium-212, it decays spontaneously. It turns into lead-208 and emits an alpha particle. So if you look at the products, lead is 208, the alpha is 4, add them up.
212 matches the polonium.
Right. And the
Yeah.
atomic numbers, lead is 82, alpha is 2, atom.
84 also matches polonium. It works. It's like nuclear arithmetic.
It really is.
So
Yeah.
that leads to the big question then. Why are some nuclei stable and others just aren't? What makes a nucleus decide, okay, time to transform? We learned the primary factor is something called the neutron-to-proton ratio.
Yeah, it's definitely not random. There are clear patterns. Our sources highlight that nuclei with specific magic numbers of protons or neutrons like 2, 8, 20, 50, 82, or 126 tend to be exceptionally stable.
Magic numbers, like particularly stable configurations.
Think of them that way, yeah. Particularly well-balanced nuclear structures. Also, nuclei with even numbers of protons or neutrons are generally more stable than those with odd numbers. And, like you said, everything above atomic number 83, plus technetium and promethium, they're all inherently radioactive.
Okay.
If you were to graph neutrons versus protons, the stable nuclei fall within this narrow band. It's often called the belt of stability. Anything outside that belt, those are the ones that undergo decay.
And if a nucleus is outside that belt, it's trying to get back in, right? So if it has too many neutrons, it's above the belt, it'll typically decay by beta emission.
Right.
This is where a neutron basically converts into a proton and an electron. So the atomic number goes up, lowering that neutron to proton ratio. Carbon-14 decaying into nitrogen-14 is the classic example, isn't it?
It is. A neutron becomes a proton, atomic number goes from 6 to 7, mass number stays the same. Perfect example. Now, conversely, if a nucleus is below the belt, too few neutrons for its protons, it needs to increase that ratio. It can do this one of two ways. Either positron emission, where a proton turns into a neutron and a positron.
Okay, releasing a positron.
Or electron capture. That's where an electron from an inner atomic orbital gets pulled into the nucleus, combines with the proton, and forms a neutron.
Wow, pulls in its own electron.
Yeah. In both cases, positron emission or electron capture, the atomic number goes down, mass number stays the same, and that neutron to proton ratio increases. It moves closer to that stability belt.
Right, towards stability.
And when we want to talk about stability quantitatively, we use the term nuclear binding energy.
Ah, okay, binding energy. This is where Einstein's famous equation E-c comes in, isn't it?
It absolutely is. Nuclear binding energy is the energy you'd need to completely break a nucleus apart into its individual protons and neutrons. And what's truly astonishing, maybe one of the biggest aha moments, is this idea of mass defect. If you measure the mass of an atom very precisely, it's always less than the sum of the masses of its individual separate protons, neutrons, and electrons.
Wait, Les, where does the mass go?
It's not gone. That tiny bit of missing mass has been converted directly into the enormous energy holding the nucleus together. That's the binding energy.
So the mass is the energy. That lost mass is the nuclear glue. That's incredible. Why don't we see this mass change in normal chemical reactions then?
That's a really good question. Because the mass defect in chemical reactions is just so incredibly tiny, it's practically undetectable. The energy changes involved are just not large enough to register as a measurable mass difference.
Oh, okay.
But in nuclear reactions, the energies are so massive that the mass change is measurable. For just 1 mole of fluorine-19, the energy released when it forms is something like 1.4 times 10 to the 10 kilojoules. That's just vastly more than any chemical reaction.
Unbelievable scale.
Right. And to compare stability between different nuclei fairly, we usually talk about nuclear binding energy per nucleon. Basically, standardize it by the number of particles in the nucleus.
Makes sense.
And here's another key insight. Elements with intermediate mass numbers, think iron, cobalt, nickel, they actually have the highest binding energies per nucleon. They're the most stable.
So iron core of the Earth, super common. It's incredibly stable, not just by chance, but because it's at the peak of this nuclear efficiency curve.
Exactly. It sits right at the sweet spot. You can't really get energy out by splitting it or fusing it, which tells you something fundamental about stability in the universe.
That is a great aha moment. Okay, let's move on to something we see in nature. Natural radioactivity. Unstable nuclei often don't just decay once and stop, do they? They start a whole radioactive decay series.
That's right. A sequence of transformations, one after another, until they finally reach a stable isotope. Uranium-238 is the famous example. It goes through something like 14 steps before it finally ends up as stable lead-206.
14 steps. And we call the starting isotope the parent and the product the daughter, right?
Correct. Parent decays to daughter, which might then decay further. And this brings us to predictability. All these radioactive decays follow what we call first-order kinetics.
Okay, first-order kinetics, what does that mean practically?
It means the rate of decay is directly proportional to the number of radioactive nuclei you have at any given time. It follows a very precise mathematical curve. And this predictability lets us define something absolutely critical: the half-life.
Half-life, the time it takes for half the sample to decay.
Exactly. And what makes this concept so incredibly powerful is that these half-lives are fixed constants of nature. They are not affected by temperature, pressure, chemical environment, nothing.
Wow, so they're like perfect clocks.
Precisely. They are nature's atomic clocks.
And these atomic clocks lead straight to dating things, right? Carbon-14 dating is probably the most famous one. How did that work again?
Well, carbon-14 is constantly being made up in our atmosphere. Cosmic rays hit nitrogen-14 atoms, zap them, and turn them into carbon-14.
Okay.
Living things, plants, animals, us, we're constantly exchanging carbon with the environment through breathing, eating. So we maintain a relatively constant level of this radioactive carbon-14 in our bodies.
Right, as long as we're alive.
But the moment an organism dies, that exchange stops.
Right.
The carbon-14 it had isn't replenished, and it just starts to decay away via beta emission, turning back into nitrogen-14.
Ah, so the clock starts ticking at death.
Exactly. So by measuring the remaining carbon-14 activity, that's the rate of decay, maybe disintegrations per second in an artifact, say a piece of wood or bone, and comparing it to the activity in living matter today.
You can figure out how long ago it died.
Precisely. Knowing carbon-14's half-life, which is about 5,715 years, you can calculate how many half-lives have passed and therefore the age of the artifact.
That's genuinely amazing. Such a clever use of this natural process. Are there limits, though? Can you date anything with carbon?
There are practical limits. It's generally not reliable for things older than about 60,000 years. That's roughly 10 half-lives.
Okay.
After that much time, the amount of carbon-14 left is just too small to measure accurately with current techniques.
So for really ancient stuff like dinosaur fossils or rocks?
For those, we need clocks with much longer half-lives. Uranium-lead dating is a major one. It uses the decay of uranium-238 to lead-206. Its half-life is enormous, about 4.51 billion years.
Cool. About the age of the Earth.
Exactly. That's how we know the age of the Earth, actually. Around 4.5 billion years, based largely on dating meteorites and the oldest Earth rocks using methods like uranium-lead.
Incredible. Okay, so we've covered natural spontaneous decay. But you mentioned earlier we can force elements to change. That sounds like alchemy.
It does, doesn't it? This is called nuclear transmutation. It's different from spontaneous decay because it's brought about by deliberately colliding two particles.
And this isn't just theoretical.
Not at all. Ernest Rutherford did the first artificial transmutation way back in 1919. He bombarded nitrogen gas with alpha particles and detected oxygen and protons being produced. He literally turned nitrogen into oxygen.
He really did it. The first artificial element change.
Yeah, it opened up a whole new field. And we use a kind of shorthand notation for these reactions: target nucleus, incoming particle, outgoing particle, product nucleus.
That's so cool. And this ability to transmute elements led to creating brand new ones, right? The ones heavier than uranium.
Exactly. The transuranium elements, everything with atomic number greater than 92. None of these exist naturally in significant amounts on Earth anymore, if they ever did. They're all radioactive and synthesized by humans using particle accelerators.
Particle accelerators,
Yeah.
like cyclotrons. How do they work?
In essence, they use powerful electric and magnetic fields to accelerate charged particles like protons or alpha particles or even heavier ions to incredibly high speeds, incredibly high kinetic energies. This energy is enough to overcome the strong electrostatic repulsion between the incoming particle and the positively charged target nucleus, allowing them to collide and fuse or react, causing a transmutation.
Makes sense. You need a lot of force to smash nuclei together.
You do. And actually, neutrons are particularly useful as projectiles for making some of these new elements. Why do you think that might be?
Well, neutrons have no charge.
Hmm.
So they wouldn't be repelled by the positive nucleus. They can just sneak right in.
Exactly. They don't face that electrostatic barrier, making them very effective for inducing nuclear reactions, even at lower energies sometimes.
Clever. Okay, from building up elements, let's talk about breaking them down for energy. Nuclear fission. That's splitting heavy atoms, right?
Correct. Fission is the process where a heavy nucleus, usually something with a mass number over 200, splits into two or more smaller, more stable nuclei. And crucially, it releases a significant amount of energy.
And why does it release energy?
It goes back to that binding energy per nucleon curve we talked about. The smaller product nuclei are actually more stable. They have higher binding energy per nucleon than the original heavy nucleus.
Ah, so the pieces are more tightly bound than the whole was. The difference is released as energy.
Precisely. The classic example is uranium-235. Hit it with a slow neutron, and it can split in various ways, maybe into strontium-90 and xenon-143, for instance. But the key thing is it also releases more neutrons, typically 2 or 3.
And that release of extra neutrons is the crucial part, isn't it?
It is, because those newly released neutrons can then go on to hit other uranium-235 nuclei, causing them to fission, releasing even more neutrons, which cause more fission.
A chain reaction.
A nuclear chain reaction. It can become self-sustaining, but to get it going and keep it going, you need enough fissionable material packed together. That's called the critical mass.
Critical mass.
Yeah.
The minimum needed for the chain reaction to sustain itself.
Right. If you have less than that, subcritical mass, too many neutrons escape without causing another fission. If you have more supercritical mass, the reaction rate grows exponentially.
And an uncontrolled supercritical chain reaction. That's the principle behind an atomic bomb, right?
Yes. In a fission bomb, you take 2 or more subcritical masses and rapidly force them together using conventional explosives to create a supercritical mass. The result is an incredibly fast, uncontrolled release of energy. The scale is just mind-boggling. 1 kilogram of U-235 can release energy equivalent to about 20,000 tons of TNT.
Staggering. But thankfully, we also figured out how to control this reaction for peaceful uses, like generating electricity in nuclear reactors.
Absolutely. Nuclear power reactors are designed to maintain a controlled chain reaction. The goal is a steady energy release, not an explosion.
How do they control it?
Several ways. First, they use moderators. These are materials, often just ordinary water, light water, sometimes heavy water, D2O, that slow down the fast neutrons produced by fission. Slow neutrons are actually much more effective at causing further fission in U-235.
Okay, so slow the neutrons down. What else?
And then you have control rods. These are rods made of materials that are excellent at absorbing neutrons, like cadmium or boron. By inserting these rods into the reactor core, you absorb excess neutrons, slowing the reaction down. Pulling them out speeds it up. This allows operators to precisely regulate the power output and prevent overheating.
So moderators slow them down, and control rods soak them up. Makes sense.
And the heat generated from this controlled fission just boils water, creates steam, and that steam drives turbines to generate electricity. Fundamentally, it's a very fancy way to boil water, similar in that respect to coal or gas plants.
But it comes with challenges. Thermal pollution from cooling water is one you mentioned.
Yes, that's an environmental consideration. And there are other types, like breeder reactors, designed to actually produce more fissionable fuel, like plutonium-239 from uranium-238, than they consume.
Breeder reactors. Interesting. But fission, overall, it's controversial, isn't it? The waste issue seems huge.
It is a major challenge. You get fission products, many of which are highly radioactive with very long half-lives. And you also get things like plutonium-239, which is itself fissionable, usable in weapons, and toxic, with a half-life of over 24,000 years. Finding safe, permanent storage for this waste is a massive technical and political problem.
And then there's the risk of accidents. 3 Mile Island, Chernobyl, Fukushima. These events have had huge impacts.
Absolutely. Reactor safety design has improved immensely, but the potential consequences of a severe accident are undeniable, affecting health and the environment for decades or longer. It raises really important questions about risk versus benefit.
So if fission has these big hurdles, what about the other side of the coin? Nuclear fusion.
Fusion, the opposite process. Instead of splitting heavy nuclei, fusion involves combining light nuclei like isotopes of hydrogen into heavier, more stable ones like helium.
And this also releases energy.
Yeah. Yes, and often even more energy per unit mass than fission, especially for the lightest elements. Again, it's because the product nucleus, like helium, is more tightly bound, has higher binding energy per nucleon than the initial light nuclei.
And fusion is seen as potentially cleaner, right? Less radioactive waste.
Generally, yes. The primary fuel, like deuterium, isn't radioactive, and the main product, helium, is completely inert. While the reactor structure itself might become activated by neutron bombardment, the long-lived waste problem associated with fission products is largely avoided.
So where does fusion happen naturally?
The sun. And all stars, really. Fusion is the engine that powers them. Inside the sun's core, at temperatures around 15 million degrees Celsius and immense pressure, hydrogen nuclei are constantly fusing into helium.
15 million degrees. That's why they call them thermonuclear reactions, right? Because of the heat needed.
Exactly. You need that incredible temperature to give the nuclei enough kinetic energy to overcome their mutual electrostatic repulsion. Positive charges repel, remember, and get close enough for the strong nuclear force to take over and bind them together.
Okay, so if we could harness fusion on Earth, the advantages sound amazing. You mentioned fuel.
The fuel is potentially abundant and cheap. Deuterium, an isotope of hydrogen, can be extracted from ordinary water. Tritium, another hydrogen isotope often used, can be bred from lithium. So, virtually inexhaustible fuel supplies.
Minimal long-lived waste, abundant fuel. What about safety?
Fusion reactors are considered inherently safer in one key respect. They operate under very specific, extreme conditions. If anything goes wrong, if containment is breached, the reaction just stops. There's no possibility of a runaway chain reaction or meltdown like in fission.
Okay, abundant fuel, less waste, inherently safer.
Sounds perfect.
Why don't we have fusion power plants everywhere?
The catch. The technical challenges are just immense. Replicating the conditions inside the sun here on Earth is incredibly difficult. You need temperatures not just of 15 million, but closer to 100 million degrees Celsius for sustained reactions.
100 million degrees. How do you even hold something that hot?
That's the containment problem. At those temperatures, matter exists as a plasma, a superheated, ionized gas. No solid material can contain it directly. So, researchers are exploring two main approaches.
Oh, sure.
One is magnetic confinement, using powerful, complex magnetic fields to hold the plasma suspended away from the container walls. Devices like tokamaks work on this principle. The other is inertial confinement, or laser fusion. Tiny pellets of fuel are hit from all sides by incredibly powerful lasers, causing them to implode and briefly reach the necessary density and temperature for fusion to occur.
Magnetic bottles and giant lasers.
Yes.
Sounds like science fiction.
It's cutting-edge science, definitely. Huge progress has been made, but achieving sustained fusion that produces more energy than it consumes break-even and beyond is still a massive engineering hurdle. We should also mention the hydrogen bomb, or thermonuclear bomb. That is fusion, but it's uncontrolled.
Right. Uses a fission bomb just to ignite the fusion reaction.
Exactly. It achieves those insane temperatures momentarily. While often called cleaner than pure fission bombs because the fusion part produces less fallout, they can be deliberately dirtied by adding materials like cobalt to maximize radioactive contamination.
Sobering thought. Okay, let's shift gears away from massive energy production and talk about more everyday applications. Isotopes, both radioactive and stable, are used in some really beneficial ways in science and medicine, right?
Absolutely. They are incredibly versatile tools, often used as labels or tracers to follow processes we couldn't otherwise see.
Tracers, how does that work?
Well, chemically, different isotopes of an element behave almost identically. So you can substitute a radioactive isotope, like sulfur-35, into a molecule like thiosulfate. By tracking where the radioactivity goes during a reaction, you can figure out things like molecular structure. In thiosulfate's case, it proved the two sulfur atoms weren't equivalent.
Ah, like tagging one atom to see what it does.
Precisely.
Mhm.
In biology, carbon-14 was famously used to trace the path of carbon atoms during photosynthesis, starting from carbon dioxide and ending up in carbohydrates. Oxygen-18 helped determine that the oxygen gas produced comes from water, not CO2. A tracer is simply an isotope used to follow the path of atoms.
Fascinating. And in medicine, this tracer idea is used for diagnosis.
Extensively. Sodium-24, a beta emitter with about a 15-hour half-life, can track blood flow and help detect clots or constrictions. Iodine-131, another beta emitter with an 8-day half-life, concentrates in the thyroid, so it's used to assess thyroid function.
What about imaging, seeing inside the body?
For imaging, you typically want gamma emitters, as gamma rays can easily exit the body to be detected. Iodine-123 is used for brain imaging, but probably the most widely used medical isotope is technetium-99 meter.
Technetium-99 meters, why is it so popular?
It emits only gamma rays, has a convenient 6-hour half-life, long enough for procedures but short enough to minimize dose, and it can be incorporated into various compounds that target specific organs like the heart, liver, lungs, or bones, allowing doctors to get detailed images of their function.
Amazing versatility. And isotopes are also used directly for treatment, especially cancer.
Yes, the same radiation that can harm cells can also be used to destroy cancer cells. There are innovative approaches like boron neutron capture therapy, BNCT, where boron compounds are delivered to a tumor and then the patient is irradiated with neutrons, causing the boron to release targeted alpha particles right inside the tumor. Or brachytherapy, where tiny radioactive seeds, maybe iodine-125, are implanted directly into a tumor to deliver a high dose locally.
Wow, targeted destruction. And how do we even detect this radiation?
A common instrument is the Geiger counter. It detects ionizing radiation and typically produces audible clicks or a reading to indicate the radiation level.
Okay, so we're using radiation, detecting it, but we also need to understand its effects on living things. It can be dangerous. How do we quantify that?
We have specific units. The fundamental unit of radioactivity itself is the Curie, CI, related to the number of disintegrations per second. But for biological effects, we look at the energy absorbed. The RAD, radiation absorbed dose, measures the energy deposited per gram of tissue.
Okay, energy absorbed, is that the whole story?
Not quite, because different types of radiation cause different amounts of biological damage, even if they deposit the same energy. So we use the REM, Röntgen equivalent for man. The REM takes the dose in rads and multiplies it by a factor called the RBE, relative biological effectiveness, which accounts for the type of radiation.
So REM is the measure of actual biological harm potential.
Generally speaking, yes. It tries to put different types of radiation exposure on a more equivalent scale in terms of biological impact.
And you mentioned different types. They penetrate differently too, right?
Absolutely. Alpha particles are relatively heavy and doubly charged. They have very little penetrating power. A sheet of paper, even the outer layer of skin, can stop them. Beta particles, being electrons, are lighter and singly charged. They penetrate further, maybe a few centimeters into tissue. Gamma rays, being high-energy photons with no mass or charge, are the most penetrating. They can pass right through the body, requiring thick layers of dense material like lead or concrete for shielding.
So alpha particles aren't dangerous from the outside, but what if you ingest something that emits them?
That's where they become very dangerous. Because they deposit all their energy in a very short range, if an alpha emitter gets inside your body, say lodged in your lungs or bones, it causes intense localized damage to the surrounding cells. Beta emitters inside the body are also a concern. Think of strontium-90, a fission product. Chemically, it's similar to calcium.
Oh no, so it could get incorporated into bones.
Exactly, and sit there emitting beta particles, irradiating bone marrow for years. That's why internal emitters can be particularly hazardous.
How does radiation actually cause damage at the chemical level?
It's called ionizing radiation because it has enough energy to knock electrons completely out of atoms and molecules it hits. This creates ions, obviously, but also highly reactive species called radicals, fragments with unpaired electrons.
Radicals. Like free radicals we hear about.
Very similar concept. These radiation-induced radicals are extremely reactive chemically. They can attack and damage crucial biological molecules like proteins, lipids in cell membranes, and especially DNA. Damage to DNA is particularly serious as it can lead to mutations, cell death, or cancer.
So it disrupts the fundamental chemistry of the cell.
Mm.
It's strange how it can both cause cancer and be used to treat it.
It is a paradox, isn't it? It depends on the dose, the target, and the control. Low doses over long periods might increase cancer risk by causing mutations. High targeted doses delivered rapidly can overwhelm cancer cells' repair mechanisms and kill them more effectively than healthy cells, hopefully. It's a powerful double-edged sword.
And this damage, it can affect the person exposed or their future generations.
We differentiate between two types. Somatic injuries are those that affect the individual who was irradiated during their lifetime. Things like radiation sickness, burns, cataracts, induced cancers. These aren't passed on.
Okay.
Then there's genetic damage. This is damage specifically to the DNA in reproductive cells, sperm, or eggs. These changes or mutations can be inherited and may affect the offspring, potentially causing genetic disorders in future generations.
That's a heavy responsibility that comes with using this technology. What an incredible journey, really, from the basic forces holding nuclei together to the immense power locked inside them in fission and fusion, and then seeing how we use these tiny isotopes for everything from dating ancient history to fighting disease. Nuclear chemistry truly underpins so much.
It really does. It's clear that while it offers almost unimaginable power and potential, it also carries these profound risks and ethical questions that we as a society constantly have to grapple with. Managing the waste, ensuring safety, considering the implications of manipulating matter at this fundamental level, it's a huge responsibility.
It really is. It makes you think.
Which raises an important question for all of us, I think. How do we best navigate this? How do we balance harnessing this power with managing its consequences?
Absolutely. And given everything we've unpacked today, the incredible energy, the stability puzzle, the practical uses, the daunting challenges of waste and safety, the promise of fusion, what new questions does this deep dive spark in your mind about our energy future? Or maybe even just about the fundamental nature of matter itself?